So, yeah, I just don't want to touch it. Okay, so I'm going to give technology is your friend. So I'm going to give some overview of some recent ongoing research looking at bistatic observations of Cabeus crater. Wes, in an obviously lack of trust that I would stick to time, has put most of the results early on in the talk, and then we back it up later on. So if I don't get to that, I can handle that in questions. Okay, so so we were the other antenna on LRO. So the key part of the MiniRF instrument was the fact that as a radar we could receive, we would transmit a single circular polarization, but we would receive orthogonal polarizations, both horizontal polarizations and also the phase information between them. And this allows us to generate all four Stokes parameters that describe the scattering matrix at the surface and subsurface, which can be used to produce a variety of scientifically useful secondary products. So the image on the bottom left shows what we did with our monostatic campaign, imaging about 2/3 of the moon. The key product that I'll be talking about today is the circular polarization ratio. And this is essentially the amount of the same sense versus opposite sense that you would receive with the radar signal. And this is an indicator of both roughness of a surface at the wavelength scale, and this was 12.6 centimeters, but also can be caused by the presence of water. There lieth the enigma. So start off with the Cabeus crater was the location of the L-cross impact, and as I'm sure everyone in the room knows, there was a very interesting result. They saw evidence for water ice amongst other species. Well, this is our monostatic result, and we didn't, which was interesting. We didn't see any. The graphs here, the lighter color, if you can see it, the gray graph is the CPR within Cabeus versus the overall south polar background of the whole for both the Chandrian-1 instrument and the LRO instrument. And they're the same shape. They're in fact slightly lower than the overall. So this was indicative that you didn't have coherent chunks of ice at the wavelength scale, which was, a little surprising given the L-cross result. So the MiniRF transmitter ceased operating in December of 2010, and since then we've been operating in a bistatic mode, where we use the Arecibo Observatory in Puerto Rico to transmit. We bounce this off the moon, and we receive that signal with the MiniRF antenna on LRO. And the key thing here is we can investigate the scattering properties as a function of beta or bistatic angle. And that's key for trying to determine whether some of the features that we see are rock or ice. So with a monostatic transmitter, that angle is by definition 0. It's the angle between the transmit and the receive pulse. But we can actually, for the first time, investigate how things vary over a range of angles. We're obviously limited to near side and polar targets because the transmitter is on Earth. And so far, we've successfully collected data on about 23 occasions. So we've targeted the floor of Cabeus on 4 occasions in the past 1.5 years. This shows that you see Shackleton crater here, and then we take quite long strips, which actually provides useful to get data outside of the key region, as I'll talk about. So these show the footprints of the 4 locations and also the angles. And note that we actually intentionally took one at almost a monostatic angle. We took it at 1/2 degrees in order to compare that with the monostatic data. Now the good thing is, so here we have just the 4 images from the 4 collects, and the second one shows the approximate outline for Cabeus. These are S1 or total radar backscatter images. By the way, what minute warning are you going to give me?
I'll give you the 2-minute warning in about 7 minutes.
Because this thing, okay. I've got 9 minutes. So the good thing is, because we take large strips of data and we have a good width to the data, There's two benefits to that. The first is you can see these images show the bistatic angles that we required, and in the middle of Cabeus, which was the target, we get the angles that we wanted, but we also naturally get a range of angles. So we've got a lot of data to analyze in bistatic angle space. And also these strips are quite long, so we have good data from regions well outside Cabeus to use sort of as a control. Now, the lighting in here isn't great, and so I will prove what I'm going to tell you with plots. But if you can see this, the important thing here is that the second and fourth images they're slightly blue as opposed to red-green. But there's no way with this lighting you're going to see that, so I will show you that in graphical form. So first of all, the background. So here we have a bunch of dots showing the locations in typical lunar highland, which we've analyzed. Closer to the equator than Cabeus. And you can see here that they are sort of fairly agnostic, relevant with angle, fairly constant CPR. And this includes the floor of Cabeus crater, which is a similar sized crater so you would to Cabeus. So here's our main result, and then we'll work backwards from here. So the triangles show analysis of the range from those four collects inside of Cabeus crater, and you can see two key features. The first is that the CPR gets much higher as you get close to a zero bistatic angle, but also at higher bistatic angles you actually have a lower CPR than the typical highland background, and this is a very interesting result. So this response is characteristic of the coherent backscatter opposition effect, which is what we predicted, which is what has to happen in order for you to see this with when you've got an ice regolith mixture. And this graph shows you is, even though these are points, Wes analyzed a 3x3 matrix around each point, so he built up statistics and he can do errors. So even with the error bars associated with this analysis, it still is a very real effect. The shape is very different to the background highland. Now, work has been done before on the opposition effect. These are two examples using optical data, but the physics isn't that different. The left is Hapke, and the right is some work done by Hapke and Blewett. The left was looking at just normal lunar regolith, and if you look at the CPR line, which is the second line down, again, you have an upturn as you get to in this, very low phase angles. And the right was some work done by Hapke and Dave Blewett looking at the polarization properties of an analog of a water ice material. And again, the top pluses, you get an uptick as you get close to zero phase angle, just like we see with the bistatic radar data. Now, so the observation of the floor of the South Pole crater Cabeus does show this response, but as we've just said, this effect, you can actually see it in optical data to do with rough material. So how can we determine that this is in fact caused by an ice regolith mixture and not to do with roughness? We can, or I wouldn't be here. So here we have sort of a control analysis that we've done using the ejector from Kepler crater, which is at 8 degrees north. So even with that interesting talk where we have the obliquity change, this has never been cold enough to harbor ice. So you can see two analyses here. The lower one, which is just like we see when we analyze the highland material outside of Cabeus. The CPR doesn't vary as a function of bistatic angle. But when we analyze the rough ejector blanket, again, you are seeing an opposition effect, but the key thing to notice is it's much more gradational. The upturn starts at much higher angle when it's caused by roughness, sort of all the way out 4, 6, 8 degrees. You're starting to get a definite trend. Whereas with what we see inside Cabeus is you only get that upturn at much lower angles. At sort of the 1 to 2 degrees is when you get the uplift. And again, that's what the physics predicts you would see if this is coherent backscatter because of an ice regolith mixture. The other thing to notice is that the CPR, these black squares lie above the background level for the mare, whereas again, what we saw with Cabeus is that dipped below and then came back up, which again is another thing that points towards the fact that it's Cabeus. So, an opposition effect is observed associated with the floor materials of South Pole crater Cabeus. Similar response is not observed for floor materials outside of Cabeus. This response differs from that observed for rough surfaces associated with the ejecta of KEPLER crater. So this, and I want to get, so at the very beginning, those of you that have stayed awake the whole time, I showed you the monostatic result for Cabeus and the fact that we didn't see elevated CPR. So we have to explain that. So this cartoon shows you the approximate difference in viewing angles. When we were in the monostatic data, we were pointing out with an incidence angle of about 48 degrees, whereas now, because our transmitter is from Earth, your incidence angle is roughly equivalent to the latitude. So you can see that the very different, our bistatic is much more grazing, whereas sort of compared to the monostatic. And so what would explain what we've seen is if you have a thin layer of ice, the path length through that ice for the monostatic data is very small. And it's feasible that you may not have had enough thickness of ice to pass through to get the coherent backscatter effect you would need to get a high CPR that we didn't see. Whereas with the bistatic data, it's a ratio of the signs. So it's about, I think it's a factor of 8 difference path lengths through a given thickness of ice, which just could well be the difference for why we're seeing this with the bistatic data when we didn't see this with the monostatic. And we're doing some modeling effort. In fact, it can go back. So yeah, Mike Zimmerman is actually talking about something else in a couple of talks. He's doing a modeling effort to see whether this makes sense. So, is this phenomena unique to Cabeus crater or more characteristic of polar terrain? So, we continue to take data about 1 or 2 strips a month, and we're targeting all the interesting large craters as they become visible to Arecibo in a good way, and hopefully we're looking for a similar kind of response. Thank you. See, I didn't have any problems.
There we go.
Okay. It's like I'm the one with all the technical problems.
Yes, you did. Just remember, it's you.
Yes, it's me. Okay, we have time for a couple questions.
I have the mic.
All right.
Good.
You
Hey,
brought
Ben.
your own? No.
Yeah. So for the CPR variation as a function of phase angle that you see in Cabeus,
Yes.
I'm just wondering, do you have the data yet, or have you looked in other PSRs to see the same thing, or do you have any inkling on what that?
We have.
Could you repeat the question, because I don't think that
Yeah.
was actually on.
And say your name.
It's on.
This is what happens when you bring your own microphone to meetings.
Okay, that's all.
Hi, Jen Heldman from Ames. So I was just asking Ben, for the CPR variations that you see as a function of phase angle for Cabeus, if you have any data yet, or if you've looked at other PSRs, or if you have an inkling if you see the same effects in other places.
We've looked at some other PSRs and don't see it, but in order to get a really robust measurement too, you really do need to take sort of 4 to 5 strips so that you can cover you really need to be able to plot over a wide range of angles. And the one downside of having Arecibo as your transmitter is you're very limited in your opportunities to see particular targets. You haven't got the freedom like you have with an orbital instrument. But we do have targets in the database to try and build up enough data so that we can do a good statistical analysis.
Okay, Paul?
Paul Hain, JPL. Can you comment on the physical state of the ice that would produce such a signature? You mentioned a layered model, but there are other data sets that seem to imply some kind of intimate mixture.
Yeah, so for example, the fact with the Cabeus, in the monostatic data we don't see it, you could have pore space filled with ice, and you're never going to see that with a radar. In order to get the coherent backscatter effect like we see, it's not an exact science, but first of all, you have to have individual chunks of ice at the few wavelength scales. So think of it as sort of basketball size coherent chunks. And then overall, you probably need sort of 10 to 15% by volume for it to be ice for you to see this.
Okay, let's do one more question.
Dana Hurley, APL. So the grazing incidence idea that you have is really interesting at Cabeus, and I'm wondering if you can comment on the North Polar craters with the anomalous signatures, if those may be indicative of thicker ice, since you saw that in the monostatic, or if that's just entirely different.
Well, there's two things. So first of all, we do, yes, the anomalous craters from the monostatic data, like inside the floor of Peary, those are probably the best case, but you do still see some of those at the South Pole as well. We're desperate to do bistatic at the North Pole. There's been, the main problem is now with LRO and elliptical orbit, it's much higher over the North Pole that makes it harder to do. And the other thing is just the viewing geometry from Puerto Rico has been such that up to now the South Pole has been better to see, but that's changing. So we do have North Polar, those